Welcome to lesson number 25, Approach to Analytical Method Validation. The overview of this lesson, we will be looking at what are the prerequisites for carrying out analytical method validation, how should you approach an analytical method validation, and a case study of a validation project. And there will also be some further reading for you. What do you think the prerequisites to validation might be for an analytical method? What do we need before we begin? And what assumptions or prerequisites are required? Prerequisites are to have qualified equipment. So we should be sure that the equipment is working properly before we start, because there's no way to ascertain if your methods are working properly if we don't know that our equipment is. The equipment must be calibrated and we must have proper glassware as well. We need to have appropriate quality reagents available. So we may need certified standards that would all have to be done in advance. We need to make sure we have the correct grade for all of our buffers and our media and for any standards or other reagents that we are going to be using. We need to have our reference standards available. They need to be properly certified and of the right quality. If we are using representative samples from a batch, we need to also have those in place. We need to have SOPs as to how the different procedures will work. What will happen if we have a deviation? How do we operate the piece of equipment? How does the method work? We need trained analysts who know what they're doing and who are competent. And we need a validation protocol that's been prepared and pre-approved. When is analytical method validation performed? It is performed before a new method is brought into routine use, or whenever the conditions change for which a method has been validated. So if we were to have an instrument with different characteristics or samples with different matrix, use a different instrument or use a different laboratory, we will need to do analytical method validation again. Whenever the method is changed and the change is outside the original scope of the method, so it's not a like-for-like change. If QC were to see that results were changing with time and they noticed a trend, we would also re-perform our method validation. The scope of the method and its validation. These should be defined early on in the product development phase, and they include the following questions. What analytes are you looking to detect? What are the expected concentration levels of those analytes? What are the sample matrices? What are we dissolving it up in? Are there interfering substances expected? And if so, do we need to detect them and do we need to quantify them? Should information that we receive be qualitative or quantitative? Do we need to be able to approximate the amount, or do we need to just detect that it's there or not? What are the required detection and quantification limits? What is the expected concentration range? What precision and accuracy do we need to be able to achieve? How robust does this method need to be? Which type of equipment should I be using? Is the method for one specific instrument, or does it need to be used by all instruments of the same type? Will the method be used in one specific laboratory, or should it be applicable in all laboratories at one site or all around the globe? What skills do the anticipated users of this method have? So how we go about performing the validation? Well, first thing we want to do is define the owners and the responsibilities. We want to define the application and the purpose and scope of method. So what is it being used for? Where is it being used? And what is the scope? Is it going to be just used on one site, across a whole organization, just across one piece of instrumentation, across all the instruments of the same type? We need to define the performance parameters and the acceptance criteria. We need to qualify our materials. So our standards reagents need to be qualified for purity. They might need to be certified depending on our accuracy levels. We need to have accurate amounts and they need to be of sufficient stability to last for the length and the duration of the validation. We must ensure that all equipment has been qualified and all of the IQ/OQ documentation must be filed. We then need to develop a validation protocol. We need to perform our validation experiments so we have a good understanding of the method. And we need to ensure that all personnel have been adequately trained and that is fully documented. We need to have our SOPs in place for executing the method routinely. We need to define our criteria for revalidating and for addressing any deviations that might occur. We need to define the type and the frequency of our system suitability tests. What are we going to need to do and how often will we need to rerun them? We need to document validation experiments and any results in the validation report. So that is the broad strokes as to how we go about performing our validation. We're going to have a look at a case study now. This is a paper that has been written, it's published, you'll have a reference to it in your appendix section, and it is entitled Validation of a Reversed Phase HPLC Method for Quantitative Amino Acid Analysis. And it just gives us a broad idea as to how we put in practice concepts that we learned in this lesson and in our previous lesson. I would recommend that you have a read of this paper so you have a better understanding. You'll remember from your school days, we would have done some simple chromatography if you did chemistry. So we would have had a little ink spot on a piece of paper, and we would have put it into water, and we would have watched as the different colours eluted from the black spot of the ink. So this is simple chromatography, have your different colours eluting at different times, so you're getting separation. Modern HPLC, high performance liquid chromatography, is based on the same basic principles. We've got our HPLC solvent, which is running through the machine all of the time, and that varies depending on what you're analysing for. We've got a pump, which pumps our HPLC solvent right around the system. We'll inject a defined amount of sample into the injector, and it'll run through our high performance liquid chromatography column. The columns then are different, so depending on what analytes you're looking for, you will be selecting a different type of column. So the idea is that the column will retain analytes at different rates, and you will end having a dispersion of peaks in your chromatogram. So HPLC also would run typically with some kind of a detector, often a UV vis, and you'd have your waste products going out here and your data acquisition, and you get a result that looks something like this, which shows you your different analytes at different peaks at different eluting times. You'll remember from our method validation what we are looking to do. We are looking to validate the precision, the accuracy, the LODs, the limits of detection, the limits of quantification, the specificity, the linearity, the range, and the robustness of your method. All of those things will ensure your method to be valid. So again, our case study is looking at qualifying an amino acid using a HPLC. So what materials and methods do we need to have in place? We need to have our mobile phase, so that's the material that is running through the HPLC at all times. That's our buffers for our solution preparation. So what are we dissolving our analytes up in? Our amino acid standard solutions, so that we know the concentration of them. Our protein samples for testing. Our instrumentation, our HPLC. We are using a HPLC with a robotic autosampler and a multi-wavelength detector. The method has been pre-formulated before we start. So our specificity. We want to make sure that our method is capable of selecting out the amino acid we're looking for. So it's calculated by comparing the retention times that are obtained in your standard amino acid mixture. So we injected 5 samples and we want to see that we've got our sample coming back out. We also use a reference protein sample, so that's 3, to just show that it's selecting our specific amino acid that we want. The minimal difference in retention times in our tests were less than 0.01, so that allows us confidence that we have a highly specific peak identification. Our linearity on our range. So we remember from our previous lesson, what we want to see is we want to see part of our linearity to be straight, and that gives us the range that we're looking for. So our linearity was studied in the range from 20 to 500 picomoles per microliter of your standard amino acid. We looked at 5 different concentration points. They were assayed in duplicate, and both the standard amino acid mixture and the test product showed good linearity in the test range. So that's passing your linearity, and it also shows you where your range is from 20 to 500. Our accuracy. So we're looking for the degree of agreement between the found value and the actual true value. So that was studied on BSA samples that were prepared from a calibrated sample. The accuracy was evaluated considering 2 different parameters. So we looked at the absolute percent error and also the recovery of your sample. The absolute percent error, the percent ABS, was always less than 7, and the average percent error was less than 2.5%. So based on the found amino acid concentration and the known composition of your BSA sample, the percent recovery of your BSA was calculated, and the range was found to be within 90 to 110% range, and that was considered to be acceptable. Precision, we're looking at your measured repeatability and your intermediate precision. The repeatability was studied on 6 different injections of the same sample, so the mean accuracy of each well-recovered amino acid was calculated. The percentage coefficient of variation, the percent CV, was within our acceptance range of 5%. Intermediate precision was studied by running the whole method on 2 different days. Each day in 3 equivalent samples were prepared and injected. And the percent CV was generally not greater than 2.5, with the exception of the one that's reported in your paper there. Quantification and detection limits. So you'll remember in our previous lesson, we looked at a number of different ways that you can calculate these. So you can use your signal to noise, or you can use your calibration curve. So this one was calculated on the basis of the standard deviation of the response and the slope obtained from your linear plot. So your calculation for your limit of detection is 3 times sigma all over the slope of your regression line, and the LOQ is 10 times sigma, your standard deviation, all over your slope of your calibration curve. So whereas sigma is your standard deviation of your y-intercept, and S is the slope of the regression line. So the values calculated then met the passing criteria. So I've got a lot of other references and further reading for you. Some of it is very interesting and gives a lot more detail about analytical method validation. They're all well worth having a read of. Please do make sure that you read the ICH Q2. So what are the prerequisites for analytical method validation? Can you identify some of the parameters you would validate in a method validation? Thank you very much for your time and attention. We'll see you for the next lesson.